I'm going to tell you today how we scaled up our Memcached cluster to 50 terabytes in size and how it improved our reliability. It's going to be quite an information-dense talk, so I'm going to move pretty quickly. The slides will be available at the end. Cool. So I like to start with the bottom line up front. So with the improvement that we made, it resulted in a reduction in object storage requests of 65%. It vastly improved our reliability of our service, and it unexpectedly resulted in a 2% TCO reduction, which was not really planned, but obviously welcome. And we surprisingly didn't see any change in performance, so I'll touch on that briefly. Cool, so hands up who here knows about Grafana Loki? Awesome, and who uses it in production? Great, okay, cool. So I'm going to talk a little bit about Loki's internals, because it'll be relevant to the content. There's QR codes in the bottom corner of some of the slides, which will take you to more information. Cool, so Loki is an open source log aggregation system, and the way that it's different from other log aggregation systems is it doesn't index the contents of the logs. Instead, what you do is you attach key value pairs, which we call labels, like in Prometheus, which identify where your logs have come from or what their purpose is, or if you extract pieces from the log lines themselves. And this helps you select the logs later, which we will then use as part of the query. We take the nanosecond precise timestamp of the log line as well, and together with the labels, we index those and store those in object storage. And the log content is unindexed, but we compress it and store it in object storage as well. This is a little representation of what log ingestion looks like coming from multiple pods, say, in Kubernetes. So we have 4 NGINX pods here ingesting logs. Don't worry if you can't read it, it's not important. It's just an access log from NGINX. So we have 4 pods here, NGINX A, B, C, and D. These top 2 are from US East 1A, bottom 2 are from US East 1B, and these unique combination of labels are what we call a stream. And based on that stream, we compress the logs down into chunks, and these chunks are given content addressable identifiers and stuck into object storage for later retrieval. And these chunks are really the unit of work, you could say, in Loki. The way we index is we associate the labels to the chunks that have been ingested by their IDs, and the way that you select the logs is you use these label selectors. So here, if we wanted to select all NGINX logs, we would just use this one label, which would select all of the chunks that have been ingested that have that label associated. If we wanted to select a subset, we just do an intersection of 2 labels to select only 2 of these chunks. So this is what allows Loki to run queries really, really fast. If we take the logql query below, which is selecting all NGINX logs from US East 1A, that's going to reduce the overall set of logs, say, from 100 terabytes down to 100 gigabytes. And then, based on a time frame, we will further narrow down the set of logs that we have to process. And then after that, we do a heavily parallelized brute force search on the log contents. So it's a trade-off. You can either index your logs up front and pay for that cost then, or you can pay for it at query time, and generally at query time it makes a lot more sense in our opinion. So here we're searching for an IP address across all of these NGINX logs over the past 7 days, and this runs really, really quickly. Now, similarly to a select star from with no limit in a relational database, you have the equivalent in Loki. So you use a regex selector here, which searches for all logs from all applications over the last 30 days, and then do a search for the IP address there. That's going to go slowly. And we call these internally needle and haystack queries. And so this was actually what started to cause us a reliability problem towards the end of last year and the start of this year. So Grafana Loki is run as a cloud service in Grafana Cloud called Grafana Cloud Logs, and it's a multi-tenant service that's deployed across 3 public clouds in 20 regions. And we've started becoming the victim of our own success recently because we're ingesting so much data and customers are running crazy queries like this that it starts to put a lot of pressure on object storage. And object storage doesn't like pressure, so they rate limit us. And so Object storage is exactly like our service. It's a multi-tenant service deployed in many places, and they have to protect their service from noisy neighbors, and we were very much that noisy neighbor. So when we get rate limited, it means we can't access the chunks fast enough from object storage, which decreases our throughput, which means slower queries. Our users get frustrated. The operators start to get frustrated because our SLO budget burn alerts start firing. And we didn't have that many knobs that we could turn at this point, besides for just slowing people down, reducing the amount of data that they could access quickly, which is obviously not great. And then we had the incident where one of our customers was doing some load testing on a cloud that shall not be named, and basically they put so much pressure on Loki, which put so much pressure on object storage, that the cloud provider thought that we were DDoSing them, and they cut off access to our bucket for 24 hours. So that was fun. So when we boiled this down, we realized we had two choices. We could either query less data or we could cache more data, right? Obviously, we want to query less data. So the way that we normally would query less data is by getting customers to improve their labels, either at ingestion or at query time. And usually this works. When you use labels more correctly, then you select a smaller subset of data to process. So we have to fetch less from object storage, faster queries, everybody's happy. But some customers are either not willing or not able to do this, and then we have problems. So we wanted to build an accelerated needle and haystack search. We wanted to improve our query engine. We wanted to look at chunk compaction, taking many small chunks, combining them together to reduce the overall number of requests to object storage. But this shit takes time. And we had a reliability problem on our hands at that point. And so, fundamentally changing the way that your database works, or adding in new components, takes a lot of time, and we needed to solve that problem very quickly. So then we're left with cache more. So this bought us time to do the right thing, and actually at ObservabilityCon next month we'll be announcing Loki 3.0, which has some new improvements, so everybody can look forward to that. So it bought us time to do that. We also now have a much easier lever to pull with caching more, because we already cache a lot. And so just by caching more, it's already there. We don't need any big architectural changes. And we can deliver this on a much shorter timeline. So let me tell you more about how we do caching in Loki. So when we ingest logs into Loki and we compress the chunks and we store them in object storage, we also prospectively store them in cache. And the reason for this is that observability data tends to skew towards very recent, right? So you're using observability data because you want to understand what's happening now, or just now, or a little while ago. And so whenever we create these chunks, we just stick them into cache because you might want to query them soon. And for a couple of other reasons, but that's the main reason. Similarly, when we query chunks out of object storage, we stick them into cache as well in Memcached. And the reason for this is, imagine you have a dashboard, and a dashboard is doing a logs query. And you have an auto refresh. You're going to fetch the same chunks over and over again. So we also write back every chunk that we've read from object storage into cache. So I mentioned that observability data tends to skew towards recent time, and this is borne out here by this graph. So what this graph is basically saying is, if we are able to cache the last 3 hours worth of data, we can serve 58% of the chunks from cache. And this is a global picture of all of the Loki instances across the 20 regions. But this same pattern doesn't hold true across all of them. And we're going to be talking about this instance, Loki Prod 3, for the rest of the talk. And as you can see, it doesn't really have the skew towards recent data. We would need to store about 4 or 5 days worth of cache in order to serve 2/3 of the volume from cache instead of going out to object storage. If we only have 3 hours worth of cache, we can only serve about 20%. And so this was really the heart of the reliability problem. We had to do too many requests to object storage because our cache wasn't big enough. But confusingly, we looked at our success metric, which is hit rate, right? Everybody looks at hit rate to see how effective their caches are, and it looked kind of okay, right? Like the average hit rate here was 70 to 90% on a daily basis on average. So we were quite confused by this. So we decided to look at it from another angle. How often was cache evicting items to make space for new items? So Memcached is an LRU-based cache. So that means that the items that were least recently used get evicted to make space for new items. And Memcached tracks evictions of items that were unfetched. And so this is like the worst possible scenario you can have with your cache. Items that are being evicted out of cache before being fetched even once. So what that means is you're storing data in cache, never using it, just wasting space, right? So we were very much in this scenario, visualized a different way. How long does it take to fully replace the entire contents of the cache? And we were doing that almost once a minute in some cases, because we were just storing tremendous amounts of volume in a little itty-bitty amount of space. So we realized we needed to have much larger caches. So how much cache do we need? This particular instance was ingesting 6 terabytes of new chunks per day. And we had initially estimated that we would need 1.2 terabytes of RAM to account for 4 or 5 hours worth of data, because based on the recency bias that we saw, storing 3, 4, 5 hours worth of data should be enough to serve a majority of data from the cache. However, because of this skew, where most of the data is being requested in the last 5 days as opposed to in the last 3 hours, you can see how woefully insufficient our caches were here. So what we really needed was 6 terabytes times 5 or 6 days in order to have enough cache to serve 2/3 of our chunk volume out of cache. The other thing to keep in mind is that Memcached is very highly networked, and we're doing a tremendous amount of volume through it. And so if we take a 7-day moving window of our P99 network usage, we were doing about 0.5 terabit per second to this Memcached instance, or to this cluster of Memcached instances cumulatively. So quite a lot. So we had to take that into account. So when we got down to it, we realized we needed about a 50 terabyte cache with 0.5 terabit of network throughput. So we set about figuring out how to build one this size. So the challenge was, how can we do this cost effectively whilst maintaining performance in an operationally familiar way? Right? There's no point in taking a reliability problem and replacing it with a reliability problem if we deploy a tool that none of us know how to run at scale. Similarly, if we run something that's expensive, that's going to ruin our margins, not going to work, and if it tanks performance but improves the reliability, then again, it's exchanging one problem for the other. So we needed all three. So this is what our Memcached was costing us. It was costing us about $9,000 a month. But the crazy number here is this number here, $4.43 per gigabyte per month. So if we were to scale our current infrastructure up to 50 terabytes, it would cost us an additional $200,000 a month. So obviously that's not going to work. So we realized the goal was to drive down the cost per gigabyte of cache. And so how do you get a large amount of space for a little bit of money? You use disks. So how can we use disks? Well, use Memcached with disks. And so not many people know about this, but Memcached has this feature called Xstore, which I firmly believe is one of the industry's best kept secrets. It evolved out of some changes that came in Netflix. And this is a fantastic blog post by Memcached maintainer. And he talks about the cost trade-offs and the performance implications. And Memcached maintainer used to work at Fastly and worked like very closely with SSDs. He knows exactly what he's talking about, and he built something amazing here. And it was extremely easy for us to use. So to give you a quick recap about how Memcached works internally, when it's all in DRAM, you've got the keys stored in one place, and then you've got your LRU data structure, which is basically just a queue. Objects come in on the head, then they slowly progress down towards the tail as new items are inserted. And once it hits the tail, the item gets evicted. If items are accessed frequently, then they move back to the head, and then only the least recently used items go down to the tail. And then we have to get rid of them to make space for new items. But when we have SSDs in the mix, now with Xstore, instead of evicting those items, we can just spill them to disk. And with a large amount of disk space, we can store a tremendous amount of chunks. So this solved our problem for us. Using XStore is really easy. You just add one additional flag. You specify where Memcached must write its data file. And you can think of the data file as just really a large amount of memory because it treats it the same way. With Memcached, when you allocate it, say, a gig of memory, it takes that gig and it divides it up into pages. It's the same with this data file on disk. It's one file divided up into page sizes, which is configurable, and you specify the overall maximum size that you can use. And you can configure it to spread across multiple disks, which is really nice. So the next question is, how do we get SSDs in cloud? And we had a few constraints here. We absolutely did not want to use a disk over network type of solution. We can't use NFS for cache. Cache is a very latency sensitive application, and so we don't want any network in the mix that's going to add any additional latency. We also don't want multi-tenancy because noisy neighbors like us don't like other noisy neighbors, and so we don't want any additional latency or jitter to be added to the mix. And ideally, we wanted these SSDs physically attached to the same hypervisor on which our nodes were running, because then that shortens the distance between our queriers and our cache. Hopefully, these will actually get scheduled in the same rack even. So that will give us the best consistency and the best performance. So Google Cloud offers what they call local SSDs, which are 375 gigs in size at $30 a month. And you can read this while I take a sip. So you can attach an arbitrary number to most machine types, up to 24 SSDs each. And these performance numbers we validated in production, so we get really good performance out of these disks. AWS does something similar. They call it instance storage. You can't specify like an arbitrary number of them or how big you want them to be. Depending on the instance type, you get SSDs of different sizes, and there's just one. And the cost is included, but the economics work out to be roughly the same. And we mostly use the storage optimized instances. You can chat to me afterwards, I'll tell you the specifics. So the time to value for this project was just 2 weeks. Because we weren't changing anything in our application, all we had to do was figure out how to configure Memcached with these SSDs, figure out how to provision these SSDs, and then test it and roll it out. And that took us 2 weeks. And this is because of the maturity of the Kubernetes ecosystem, the clouds that we're using, and Memcached. And yeah, it was just really easy to roll this out. So this is the new setup that we have. So we have 33 instances instead of 200. Each one has got 4 SSDs. So that's 375 times 4, 1.5 terabytes each. So that gives us our 50 terabytes of disk. Each of these nodes supports 16 gigabits of network throughput each, so that gives us our half a terabit. And you can see that this actually comes out to be cheaper than our previous infrastructure, which blows my mind. And it's because of this number here, 8 cents per gigabyte per month. That's a 98% reduction in the cost per gigabyte for our cache. So, this is what we were running before. So the TCO benefit that I mentioned at the top of 2% doesn't come from us saving $100 here, as you'd imagine. It comes from improving the request to object storage. And that's because we store billions of files in object storage. So reducing that volume down significantly really helped a lot here. So nice side effect. All right, so let's get into the numbers. So rate limits. Obviously, as we were expecting, went down because we were able to cache a lot more. We do see a couple of spikes here and there, but in general, it's not a daily occurrence. So that was looking a lot more stable. The all-important number, the SLO, or the SLI, was looking a lot healthier. So instead of being consistently out of SLO before, following the rollout, we were consistently in SLO. And this is the query throughput SLO. So this is, are we processing queries fast enough? Hit rate improved. So now we're looking at a daily average of about 95% hit rate. The churn rate has also massively decreased, so the number of items that were unfetched and being evicted went down, not to 0, but to a very manageable number now. And based on how many chunks we're requesting in our queries and the amount of volume going through these chunks, these unfetched evictions are kind of unavoidable, but at a manageable rate, it's very acceptable. So this is probably the graph that represents the results the best. The green line, yeah, I guess you can read the units there. The green line represents the volume of data in terabytes that we were fetching from the cache, and the yellow line is how much we were fetching from the store. And you can see before the rollout, they were basically, the same number because our caches were ineffective, they were too small. And then following the rollout, you can see this very clear separation where our caches are now fetching almost an order of magnitude more data, serving an order of magnitude more data from the cache than fetching from the store. Query performance wasn't affected, but it was maintained, which we were happy with. And the reason why the performance didn't improve all that much is the bottleneck is clearly not in our data access layer right now, but we have some performance improvements that are hopefully coming soon that will allow us to realize some of those results too. And then everything was perfect at the end. No, trade-offs everywhere. I hope everybody's familiar with these latency numbers. So now we went from a cache focusing, based mainly in main memory, now to a cache that's using a lot of SSDs. You can see there's a large difference here between these two latency numbers. So obviously we would expect to see the latency go up. So this is the P50 latency of our Memcached cluster. You can see we went from low single-digit milliseconds up to sometimes 50 milliseconds at a time. But this was entirely tolerable to us because in yellow, this is the store's P50 latency. And as you can see, going out to object storage, even the best P50 is always worse than our worst P50 from cache. And with object storage, we can only fetch one item at a time, whereas with Memcached, we can do batches of requests. So this was something we were happy to tolerate. SSDs in the cloud are not entirely durable, and you have to keep this in mind. We really just treat them like large, DRAM instances. Our cache was volatile before; it's still volatile now. But while the node is running and while that SSD is up, then the data will be durable, but there are a bunch of scenarios in which that data will be lost. It's completely fine to us. We architected the cache in a way that losing one node at any particular time would only lose about 3 or 4% of the cache. So we can lose quite a few and then just rebuild the cache up passively. Of course, as any sysadmins in the room will know, as soon as you add disks into any system, everything just goes to shit. So disks can fill up, they get bad sectors, they get hit by cosmic rays, whatever, and they age out and start to perform poorly. We've got monitoring for this, and when it happens, we just kill the disk. People say that the cloud is just someone else's computer, but also it's someone else's problem. So, we just drain the node on which these disks exist, and then we just recycle them, give them back to the cloud provider. They either drill a hole through it or they recycle it somehow, and they give us a new node with some new disks. So problem solved. We don't care. It's just cache. Obviously, being from Grafana Labs, I'm an observability acolyte, so I have to mention, Prometheus and an alert manager were absolutely essential for this project, as were Grafana and Loki. We really couldn't have done it without this project, honestly, and we built pretty dashboards like this to visualize the progress. Before I shut up, I just want to leave you with a couple of thoughts. Now that we have SSDs that are quite, cost competitive, and they're very large, and they're approaching DRAM speed, maybe this is going to start changing some of the, widely held beliefs that we've had about splitting to disk. The latency cost that we pay by splitting to disk. Now maybe those are being lifted, which is quite interesting. Network throughput is also growing quite nicely now, and there's some new CPUs coming out that are dedicating chiplets, I think, to handling software-defined networking. So Those two things together mean that spilling to disk might not actually be such a penalty as it was before. So the slides are available over here. There's a blog post with a lot more detail on the Grafana Labs blog. And shout out to my colleague Ed Welch and the maintainer of Memcached, Alan, who helped a lot with this. And thanks. I'll take any questions.